So welcome everybody to the lectures on quantum theory. As you know, this is an integrated course that will be taught in half by an experimentalist, Stefan Götzinger, and in half by me for the theory side of quantum theory. And the two parts are obviously complementary, so we make a big effort to harmonize the teaching of these two, but it's not perfect. And in fact, it shouldn't be perfect, because then we would sacrifice the respective contents for the harmony of the two lectures. So as always, it will be partly your task to bring things in harmony by thinking about them, working on the problems, and so on. Nevertheless, having said that, the parts try to be in harmony, because after all, it's the same subject. Now, quantum mechanics has a reputation for being very difficult, and it really earns that reputation. It is very difficult. It's very difficult conceptually because, unlike classical mechanics and maybe in part electromagnetism, it really is very different from what we usually feel how the world is. The point is that feeling is wrong. The world isn't like we feel it is in classical mechanics. And then the reason is, why does classical mechanics work so well? And the answer is because the masses involved in classical mechanics are comparatively large. In fact, not even for the stone that you throw, it doesn't simply follow a trajectory. It doesn't. It doesn't follow a trajectory that's governed by Newton's axioms. It doesn't follow a trajectory at all. Even the idea of a particle following a trajectory turns out to be entirely wrong. Now, you all know the double-slit experiment. You probably heard of that, right? In school, who knows that? Everybody, right? So, in a sense, investigating or thinking about what the result means, it means that an electron that you shoot, an individual electron, neither goes through one slit nor the other. In a sense, it goes through both slits and through none. It's very complicated, okay? But the same is true if you would take a whale. So you make a double slit, sufficiently big slits, and you shoot a whale, a fish, all right? Well, it's not a fish, but nevertheless, a big thing, right? You shoot the whale, and the whale neither will go through one slit nor the other. It's just that, well, so people did this up to molecules with, I think, 800 and something molecules. I hope that's right. Well, roughly that's right. It's the theory part, okay? So it's, it's roughly right that you can do this with very big molecules, not only with electrons. So the effect is there. It just becomes more and more difficult to set up the experiment and to really see the effect, because the effect becomes the smaller, the bigger the masses of the objects involved are. But it's wrong for whales. Classical mechanics is wrong for whales. It's wrong for electrons. It's simply wrong. It's totally wrong. Now, people discovered bit by bit what was wrong with classical mechanics, and we will not follow this historical approach. Anyway, it would be pseudo-historical, right? Going through one experiment and you think it works like this, then you go to the other, and it also confuses one's thinking. We can afford the luxury. We have a well-working theory of quantum mechanics. Well, I'll start actually writing down what it actually is, what we want. So, say section 1, the educated term for what you want. Okay, so you want several things. Quantum mechanics, thereby I mean the theory of quantum mechanics, needs to account for, I avoid the term explain, needs to account for several things. And I'll mention 3. And the first one is that measurements of observables range, unlike in classical mechanics, not only over some interval I in R. So I underline this whole statement And I'll give an example for that. So first of all, in classical mechanics, I remind you, an observable was a map F, that takes an element of the phase space, which in most cases is given as the cotangent bundle of some configuration space, phase space, the Q's and the P's. It takes an element from phase space, which are the states of the system. If you know an element in here, you know the state in which the system is, which is exactly the information you know in order to evaluate each observable of the system, and takes this to the real numbers. And because it's classical mechanics, these maps at least are continuous. All right? I mean, usually you want them to be differentiable and so on, but they're at least continuous. What does that mean? Well, if you have the entire phase space here, and you equip this with the standard topology, and you have a topology on here, it means you can only, the image of this F will always be an interval on R. It cannot jump. So this continuity means that if you look at all the values this F could take for all the states, so I plug the whole set in, then what you get is an interval because of the continuity. Okay? It's not possible, for instance, for the energy to get energies from 0 to 20 and then from 40 to 60. It's just not possible because of this continuity. So consider, for instance, the two-body problem. The two-body problem for a potential, all classical mechanics, right? For a potential, V of R goes like -1 over R. So the typical Kepler potential, or as you met it in classical electrodynamics, the electrostatic spherically symmetric potential, the Coulomb potential. So you know that if you have a two-body problem, that you can reduce it to a one-body problem with an effective potential, V effective, which then, if the angular momentum of the system is not 0, will look roughly like this. For angular momentum L non-zero, you have an effective potential like this, right? And so this is the relative coordinate between the two, there's no color, between the two bodies. And now you know, of course, if you're here in this two-body problem, it's reduced to a one-body problem, then the system doesn't move, and that's the circular motion. So this is the exact circular motion. Now, if you have an energy, so this is the effect, if you have a total energy that is like here, then the system will have, the particles will have relative distance between this R minimal and this R maximal. So if you have an energy like this, so this was the energy for the circular motion, if you have an energy like this, then you get elliptic motion. And that it's elliptic motion that discloses has to do with this being a 1 over R potential. Okay? Now, if you go to this energy here, which here happens to be 0, then you actually get the parabolic motion. So it's already scattering of one particle on the other. And if you go to even higher energies here, then you can run in from infinity, you run out, and you never come back, the same as here, but it's no longer parabolic. It then actually, so parabolic is a little bit more like so, but then you actually get hyperbolic. Then you have the hyperbolic motion, right? So this is what happens classically in a two-body problem. And if you look at all, and my point is I want to come to, so the whole system has a total energy given by the Hamiltonian in classical mechanics. And if you now look at the values here that the Hamiltonian can take, then you see the Hamiltonian for any of the state of the systems. What values can it take? Well, any value starting from here, okay, up to infinity, right? These are all the values it can take including this one. So it takes all the values from an E minimum to infinity. And that's, of course, an interval in R. Okay? So this is an example. So you have a classical system and an observable, like, for instance, the energy, but we could take any other observable, will take values in an interval. A big interval, maybe the entire real axis, maybe a finite interval, maybe a half-infinite interval. It will always take values in an interval. That is what classical mechanics predicts. And it doesn't matter whether this is a gravitational potential or whether it's a Coulomb potential. So due to the electromagnetic interaction, you will always get this result. And so for any other classical problem you look at. So given this situation, it's quite understandable that if one makes a model of an atom as having a nucleus that's positively charged and a number of electrons outside the nucleus that orbit the nucleus, and in the simplest case, the hydrogen atom, for a simple model of a hydrogen atom consisting of a positively charged nucleus and an electron orbiting this, where you then take the electromagnetic interaction. If you think of this classically, you get exactly the picture over there, and you would expect to get all possible energies, starting with a certain minimum energy, any possible energy, because it's an interval, up to infinity. So if we draw the classical potential, okay, so this is what we intuitively would say, well, that's exactly the case we look at over there. But then you make a discovery, you actually measure this. So this is measurement. And you make a remarkable observation. Well, first of all, for the hydrogen atom, with this being the electron and hence having the mass of the electron, and this being the proton having the opposite charge and the mass of the proton and so on, you get here minus 13.6 electron volts as the lowest energy. Well, that's just because it's a very special system. It has a very special E minimal. But then the next possible energy is not one a little bit higher or a little bit higher, but the next one is already only a quarter of this into the negative domain. So if this is half, only a quarter here. That's the only next possible energy the electron can have. How on earth? Well, that's the case. It's the measurement tells you that. Of course, you get this by looking at spectra of electrons that go to the next level, and then, of photons that are emitted if you fall from one level to the other one. Okay. Then the next one, okay, so I write it down, so there's a formula for it. The energy, there are only discretely many energies in the negative domain. It's minus 13.6 electron volts times 1 over n squared. So for n equals 1, it's this one. So for n from n star, so without the 0, n equals 1 is this. N equals 2 is only a quarter of this. N equals 3 is only a ninth of this. So you see it gets very quickly very close to here. That's the next possible energy. The energies in between are simply not assumed. Big question mark, but that is what you see in nature. And you can see this here, there is an accumulation point. If you continue with n to larger and larger integers, you come closer and closer to 0, and 0 is an accumulation point. And then, well, that's only for the negative energies, and from then on, there is a continuum of energies. From then on only, so this energy, this energy, this energy, and many more. And from there on, there is again all energies up to infinity, which corresponds to the scattering state. So if it's not a bound state, that the electron is bound, if it's not caught by the nucleus, then you can add infinitesimally more energy, and that also exists. As soon as you scatter, it's continuous again. So that looks more familiar, but what does it help? I mean, there is this discrete stuff going on which simply doesn't possibly fit into this idea of an observable, in this case of the energy. It's a big, huge question mark. Okay? So this shows there is something going on here. The conclusion is, so it's conclusion A, because this was item A for which we have to account. We need entirely new mathematics in which a notion of observable can be defined that allows for a spectrum of measurement results and I use here the word spectrum in a colloquial sense, well, the whole spectrum of things, right, of numbers that can come out for an observable. But in fact, it becomes the technical terminology. We will call this a spectrum later on. A spectrum of measurement results for an observable. And let me call the observable A. I could also call it F and put a hat on it. That's the standard thing that people take this F and put a hat on it and say, this is the classical one. With the hat, it's the quantum one. But because we do a lecture on quantum theory, we have hats then all over the place, so I don't do that. And it also suggests that somehow from the classical one, you could construct the quantum one. One might call this quantization. Well, that doesn't really fully work. Okay, so let's not think of that. Let's think of an observable A. Let me call it a quantum observable A. And what exact object that is, using what mathematics, that we will do. Okay, I'll do actually in the second part of today's lecture. That takes the form, so the spectrum that takes the form You freely interrupt me. So if anything is unclear, you just speak your mind. You don't need to wait for me to pay attention to you. You just talk. If it's too much, I'll stop you. I mean, this is small enough. We should have a discussion of sorts. Okay. That takes the form. So we say with an observable, there should be associated a set of possible measurement results. And that set should consist of a discrete part union with a continuous part. So we still have this continuous part of the possible measurement results, but somehow we need mathematics in which we can write such an object A, such that associated with it is the set of all possible measurement results. And this is very non-classically mechanical. So remark, and I mean, so far, these are only symbols, but these symbols will appear later on in the formalism, in the mathematics. Of course, I could start out just doing the mathematics, and then the symbols appear, and then you don't know where the whole thing is going. So hence, I'd rather tell you what it means physically, give you an example, you have a picture in mind, but we'll soon enough come to the very precise formulation. Okay? You will wish we come back to here. Okay, so it's a discrete. So remark, there exist examples of systems where now I just draw pictures to be quick, right? Where certain observables, I mean, this could be the energy or any other observable, and each observable has a different spectrum for a particular system. You can have, and now I draw what was here the vertical axis. I draw it like this. So we had, for instance, this here, we had the smallest one. Then we have something that goes geometrically, something like this, accumulation point. And then you have a continuous spectrum from here. And that's e.g. the H atom. We just had this. I just write it down again so that you can compare the pictures. We could have another system for another observable, right? I mean, other system, other observable. Other system, other observable, whatever that is mathematically yet. You could have, for instance, that you start with, I don't know, why not with zero energy, or let's say with, well, if I say zero energy, there must be a scale and so on. Let's say with some mysterious number h bar that has action dimensions and a frequency, something like this. And that then goes in equidistant steps, ta-ta-ta, up to infinity. And that would be, for instance, the quantum harmonical oscillator. The quantum simple harmonic oscillator, right? So with a Hooke law or whatever. But then the energies really start here and go up like this. So this is totally impossible classically. Here this part looks classically, but anyway you have this. But then you can also have yet another system, yet another observable, or maybe, sorry, that would be the energy. So in each case, sorry, this would always be the energy for this system. So let's say other system, not other observable. But for other observables, it's the same. Let me, for fun, for the simple harmonic oscillators, also do the position observable. We call it Q. So you now do the harmonic oscillator, and you don't ask what are the possible energies. Well, the possible energies, well, we'll calculate this at some point, but I now already tell you. The possible energies have, is that right? Something like that. So the possible energies look like this. Now, but what about the possible positions of a quantum harmonical oscillator? Well, it turns out the possible positions are all. So it can be that for a system that's a quantum system, like the harmonic oscillator, so both of these are the harmonic oscillator, quantum harmonic, simple harmonic oscillator, that some observable is quantized, right, has these discrete, but you shouldn't use this word, is this discrete spectrum. But another observable, that's also of interest, namely, where is the particle? Well, it could be anywhere. We'll be able to learn more about this, but it's not like all observables are necessarily then have such a discrete feature, right? I'm just pointing this out. I'm just giving you encyclopedic knowledge, right? I mean, nothing I say you can understand, you must accept. So we have a few examples in mind so that later on we know where the whole thing is going, okay? So we have this. Now let's do yet another system. Let's take the Hamiltonian of a simple model of a solid body. So a solid body you can think of having consisting of many atoms, let's say in one dimension, and then there is an electron that can travel along this, something like that. So you have a periodic potential in which the electron moves, periodic potential, if you thought about this classically. And then you will find that depending on the details, of course, but then you will find that there will be bands of possible energy. So there will be several intervals, right? This is always closed. So there will be several intervals. This is still not classical, because classically the energy, because of the continuity of the observables, would have to be one interval, the possible values. It couldn't just jump one interval, then you make a jump, you go to another interval. So although this looks almost classical because it has no isolated discrete values, this observable, also this is only possible quantum mechanically, right? Etc., etc., etc. And there are also examples where in the continuous spectrum you still have an extra discrete one embedded. Yes?
Are those open intervals? Or?
No, these are closed, so it turns out that the spectrum of an observable will always be a closed subset of the real line. That's the result we are going to get. Okay? Hence I drew it like this. In the standard topology, closed in the standard topology on the real line. Okay? Good. So all of this is possible. And, well, so this looks like a terrible task to construct mathematics that actually can do this and can also do the other two things I'm going to say. And we'll come to talk about that in the second half of today's lecture. Yes? Yes, sure.
You could use also the network behind them that we're using right now.
Yes.
And lift them.
Yes. That's true, but that's constrained by other considerations such as the camera operating properly and me keeping track of where the blackboard is, because I devote my entire attention to you. Let's do it like this. I know, it's not ideal, but that's why we changed rooms. So this blackboard is even better than still better than the other one. Okay. Well, second remark, and that's in a sense that points to what we're going to do later. It turns out that self-adjoint linear maps on a complex Hilbert space will be a suitable structure to describe or model observables in quantum mechanics. So that means that the H's and the Q's and the A, whatever I wrote down, these are going to be self-adjoint linear maps on a possibly, and in most examples, infinite dimensional complex Hilbert space. What that is, we'll come to that. I just point to that. So the big mystery, what is this? If it's not a map from the phase space to the real numbers that's continuous, like in classical mechanics, what is it? It's a self-adjoint linear map, and it will be used in very different ways than we use the classical observables. Nevertheless, they take the role, whatever is left of the classical idea of measuring things and so on, is encoded in these objects, but in a very different way. It's not that the domain are the possible states and the target of these linear maps are the possible measurements. No, it's not like this. But this is the right structure that encodes all the information. Okay? How exactly that works, we'll set down as axioms. Okay, so anyway, we have this issue of the possible measurement results that we see in many, many, many experiments that simply cannot be accounted for by classical mechanics and the notion of observables there. So that needs to be changed. B, so quantum mechanics also needs to account for an irreducible, it's not in a technical sense, an irreducible impact that each measurement has on the state. We haven't talked about states in quantum mechanics yet. On the state of a quantum system. So, if I ask the question and I think of you classically, and I ask what's your momentum right now, in whatever frame and so on, what's your momentum, there's an answer to it, and it will not change your momentum. It will also not change your position. It won't change your state at all. In quantum mechanics, remarkably, this is not the case. And let's look at a very concrete example. So usually this is done with uncertainty relations, and of course it has to do with that. But the crucial example, the crucial experiment, I'd rather say, is the famous Stern-Gerlach experiment. What do you do in the Stern-Gerlach experiment? Well, you take an oven. So it's like a pizza oven, it's like this. And in the oven, unlike in the pizzeria, you heat silver atoms. You heat them. and then they're emitted from there because you put a little hole in there. And then you take a screen with one little hole so that, in a sense, the silver atoms come out of there. And then you subject them to an inhomogeneous, that's very important, you subject them to an inhomogeneous magnetic field. The question is who gets such ideas, but anyway, you do this. An inhomogeneous magnetic field, whatever you need for that, you need something like this here, and then like this, and you run currents through it and whatnot, whatever you need to do. Ask the experimentalist. You produce an inhomogeneous magnetic field. And you send this stuff through. Now, well, we can just do the experiment. I can't tell you the outcome. It's more humiliating to think about what would happen and then to see that it doesn't happen. And so in order to subject ourselves to this humiliation, we make a simple model of silver. And the simple model of silver is that it has a core with many protons and neutrons, as we would say, and it has 47 electrons out here. And of these 47, 46 arrange in such a way that that their spin doesn't count. So it's 46, but the 47th electron out here gives the whole thing a magnetic moment. Okay, what's a magnetic moment? A magnetic moment is something that contributes to the total energy. So there's a energy part for this whole thing, but then there is a part where you have the magnetic moment of this whole thing times the magnetic field. You have a term like this. Did you see this in electrodynamics? Magnetic moment and coupling, yeah? Something like this. So you have something like this, and if the whole thing worked classically, then you would expect in this oven for all possible kinds of magnetic moments to be there, because it's just an accident how this electron is arranged and how its spin is arranged, okay? Now, because this adds to the energy, you shoot this through here. See this? Okay. You shoot this through here. You can look at the screen what happens. And because there's a distribution and statistical and blah, 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 you expect that you get an impact pattern that looks a little like this. So the ones that are a little bit deflected to up here have their magnetic moment like so. The ones down here have it like so. And all the others in the middle, there's kind of a projection in this direction. And you get kind of a smeared picture like this. Okay? Because it couples to this inhomogeneous magnetic field, because if you take derivatives to get the equations of motion, you get derivatives of the B, hence it needs to be inhomogeneous to contribute at all. Okay? You expect this. So this is the classical expectation if you have the simple model of the silver atom. The point is, the problem here is not going to be that this is a simple model. This is a good enough model. Okay? The point is that this is not a classical system. Well, nothing is a classical system, as I said. Not even a whale is a classical system. So you could heat whales and send them and so on. Okay, well, of course, not so simple. But okay, so it goes through here. Well, it's important because one often talks about the classical system and the quantum mechanical system. Well, there is no classical system. Okay, the classical system is what we call a classical system and think of as a classical system. But you and I and the blackboard and the universe system, they're all quantum mechanical, as you know. Okay. Now, so you get a spectrum like this. Now, however, what really happens, the experiment shows something different. The experiment shows, so I draw the same screen, but it's really just replacing this screen. The experiment shows there's impacts here. Well, it's a bit distributed because it's experiment. And there's an impact here. There's absolutely no impact in the middle. In fact, you only get either this type or this type. How is that possible? Okay, I mean, this is really a big exclamation mark. This is outstanding. What, right? So for future reference, this is the hard result, and this is the W tau phi result, right? So you say, what tau phi, right? I mean, how is this possible? And you say, well, it's again this quantum mechanical issue. Observables, in this case, the position of impact, is discrete rather than an interval. Okay, we already know. Yes, that's right. So it's again this discrete thing. So why do I give this example here? Well, because this apparatus is so nice, we can learn even more from this. So this is not the surprising bit, okay? But this is also what happens. The surprising bit is what comes now. So again, this result is at this point not to be understood. It's just to be noted that there is an issue. Because classically, we need to expect something different. Abstractly, because it couldn't be discrete values because of the continuity of the observable maps, of the maps that represent observables, but also not experimentally. It's simply not the case that comes out what the classical physicist would expect. So again, this is not the so remarkable result yet, although it's again another instance of this quantum mechanical behavior. But this becomes very interesting if one considers a succession of such Stern-Gerlach apparatuses, right? So let's draw this a little more schematically. So we shoot silver atoms into a Stern-Gerlach machine, which is essentially, I need color next time, which is essentially this machine here. Okay? And so we shoot you see? So it's essentially this machine. So we shoot something in, and then, well, in reality, two things come out, namely this one or this one, okay? So if we do this, either one type or the other type comes out. What you shoot in goes either up or down, okay? And I should mention that this inhomogeneous magnetic field, you can, of course, take this apparatus and orient it in different directions. Maybe you have to drill a hole through here to send it in and blah, blah, blah. But you can orient this in Z direction. Let's say this was in the Z direction, but you could also rotate the apparatus and orient it in the X direction or in the Y direction. Again, I don't know why people do that, but if you do that, you could take this SG1, but let's first not rotate it. And what you do, whenever this here comes out, not whenever, but where this comes out, you put a little block. So you say, okay, I block this out. I throw this away. And then you arrange the next apparatus such that only the upper thing is fed into there. So we could call this, if the apparatus is oriented in the Z direction, we call this the Z plus or the Z up. There was one symbol. It's the Z up silver atoms. And down here, these are the Z down silver atoms. They just need a name, okay? And then you feed the Z up ones in another Stern-Gerlach apparatus that's oriented in the same way, that's oriented in the Z direction. And then what we will see is that only Z ups come out 100% and no Z downs come out. You say, well, of course, I filtered them out, right? It's not surprising, okay? It's not surprising. You say, yeah, well, I took them out and then only the Z ups are left. And then doing the same again yields nothing new. And, okay, no surprise. Okay, so let's do something different. Let's take the Stern-Gerlach apparatus in the Z direction. Let's block out the Z downs and let's only go through the Z ups. And now we take another Stern-Gerlach apparatus and we now orient it in the X direction. So it's the same box, just oriented a different way. It goes to different way. And now what you get is, of course, a splitting in X up and X down. If this was the X, Z up, Z down, but X up, X down is the same thing. Okay. How much of which? Well, it turns out experimentally, so I should really emphasize this is all experiment. What comes out is 50-50. You say, okay, not such a big surprise because we have many these, and then we filter out the ones that have the z up, but apparently in the x direction of these z ups, still 50 have an x up and the other 50 are x down. What does it mean to be x up or x down? It means if a Stern-Gerlach apparatus is put there, these are the two that come out. You see? So the meaning, and this is very physical, you see. In physics, you have always to ask, if you call something x up or x down, how would you measure whether it's x up or x down? Notions in physics need to be defined, the central notions, by measurement prescriptions. Well, I call something an x up if I feed it into a Stern-Gerlach apparatus oriented in the x direction, it comes up here. It comes out here rather than here, okay? That's the whole meaning of x up, x down. And we want to figure out what does it mean to be z up, z down, x up, x down. Anyway, this is still, okay. But now comes the big surprise. So we start the same. We take the SG in a z direction. We block out, because we want to, the z down direction, only z up. We feed this, like before, into an SGX, that's fine. Then there come out x ups and x downs. And we could have the idea that we filtered out the z downs, and of the remaining z ups, 50-50 are x up and x down, that's right. And we could think now we're in a sense in a quarter of the possibilities, because if we now we block this one out again, and we feed this into here, and this is again an SG in the z direction. Z, then x, then z again. And if our idea of things being filtered out and just measured what is are true, then there are only the z ups left, there are only the x up left. So one would expect that something like only z ups come out. But that's wrong. 50-50, again z downs come out. Why is this remarkable? Well, didn't we filter out all these ones with the property z down? They were filtered out. Then the z ups share this property up down, x up, x down apparently. And all of a sudden the z downs appear again. What does this mean? Well, one can analyze with this Stern-Gerlach thing, one can analyze lots of stuff. And actually somebody who doesn't take it to an extreme, there's other literature in this, C. Sakurai, Modern Quantum Mechanics or something, Sakurai's textbook, for further conclusions one draws out of this. I just want to draw one conclusion out of it. The measurement must have an impact on the state, because otherwise, if this was just a filtering, looking what is, I just take the ones with z up, how would all of a sudden z downs be there again if I only took z ups? Our conclusion that we draw from it, so that's conclusion B, measurements. Why is this a measurement? Well, because I can decide what I fed in, whether it has this property or that property. Measurements have or change the state of a system. And now there's this usual question, well, in classical mechanics too, in order to look where something is, you have to shine some light on it, the light gets reflected, you collect it. I mean, that's how I see you, right? Sunlight comes in, it's reflected on your forehead, goes to my eyes, I see you there. It's kind of some radar principle, okay? And in principle, the radiation pressure of the sun pushes you a little bit away from where you are, okay, in principle. But then I use less and less and less light, and I push you less and less and less. The beauty of this is because it's only up-down, there is no being a little z up or a little z down. There is nothing to be done, okay? So this is really from this, you see this like in no other case. This is not a matter of experimental precision. This is just a fundamental thing. Measurements change the state of a system, which means in a quantum system, you cannot simply look, and after you looked, you learned something which is then still be true, but you look, and whatever you learned afterwards, what was true before, in a sense, the state before is not the state after looking. it's a mess, right? This is terrible because, you see, this is not what we expect. It's not what we would like, but that is how nature operates. Huh? Okay. So, well, we need to accommodate that in the theory. That's the second bit here. Okay. I present one more thing we desire, and of course, a complete analysis of all the experiments that are there and what you could learn from them and could be conducted, and some people try to, in a sense, derive quantum mechanics, the formalism, from all the things you observe. One can do this, and this probably takes a whole semester, and it has an appeal. However, a theory is always more than just the predictions it makes. Maybe you remember from classical mechanics, you can describe gravity as a force, Newtonian gravity as a force. You can alternatively describe it as a curvature of Newtonian space-time. Both yields the same results. Okay? So the question, is gravity a force, is more a choice you make of how you write it down rather than an insight about nature. So it means a concrete theory you write down is always more than the sum of its predictions. Or like some people say, for every phenomenon or collection of phenomena in nature, there's usually a whole number of different possible descriptions that all yield the same result. So the theory is more than the results it yields. Hence, it would be very difficult to derive a certain formulation of quantum mechanics, probably impossible, to derive a certain formulation, mathematical formulation of quantum mechanics from the collection of phenomena, because that's simply not uniquely determined. Okay? So we're not following this approach. Nevertheless, I want to introduce a third desideratum, and then I will resolve the whole business by writing down the axioms of quantum theory already in the language we're only going to develop. So this is the next step of frustration, okay? However, it will not be entirely without insight, because the key definitions I will already provide, and I will provide them in the final version. So it's not a simple version of quantum mechanics. There are also many books that feel they must first provide a somehow correct theory, which is not properly correct, and then they refine this with time. We're not going to follow this approach. We're writing down the axioms from the beginning in the final form, and we will then work hard for the first half of the course. We will work hard on understanding the mathematics that are needed to work with this, to understand it, and to work with it. Okay, but before I come to that, the third thing we want is the following. So we need to accommodate fact C, that even if the state of the quantum system, and I haven't told you yet what I mean by a state, I appeal to your physical intuition, which is very dangerous in quantum mechanics, but we'll have the axioms later on. Even if the state of the quantum system, so call it the state rho, it will later on always be called rho, even if the state rho of the quantum system is completely known, could be, for instance, so not completely known would be some mixed state that you only know some statistics about it, but even if the state of the quantum system is completely known, the only prediction one can make for the measurement of some observable A is that the probability, nothing but probability you can predict, is that the probability that the measured number measurement apparatus always gives you something, 20 joule or something like this, that the measured number, which you know must be in the range of possible measurement results, in the spectrum of the observable, is the probability that the measured number lies within a Borel measurable set E, subset E of the real numbers. This probability is, as I said, calculable, predictable, calculable, denoted, it gets a name. It's called mu because mu stands for measure. Did you do measure theory in mathematical? No, you didn't. Okay, we are going to do that. So the basic idea is the following. If you have a set, and in our case it will always be the real line, and on the real line there will be parts that belong to the spectrum, okay? And what you want to know is you want to have a measure, roughly speaking, a volume of all possible subsets of the real line. And it turns out that no such notion of volume exists, such that with certain assumptions of translation invariance and blah, 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 such that you could assign to every subset of R consistently a volume. You cannot. You have to define a so-called sigma algebra. Never heard that term? Okay. You have to define a so-called sigma algebra, which then encodes the so-called measurable sets to which you can assign a volume, and then the measure is the volume of that set. It is and that leads to the Lebesgue integral. Did you do the Lebesgue integral? Aha. How? Okay. Okay, good. But okay, so I'll have an extra lecture on this. It's not a problem. We'll no. But the point is, you ask for a certain observable, and for a certain state, you get such an object. This object is called a measure. That's a mathematical notion. And then you can evaluate the measure on a measurable set. And if you do this over the real numbers and you construct these measurable sets in a certain way, they're called Borel measurable sets. It's a special implementation. It's a little bit like the standard topology, so you have the Borel measure. Okay? This probability is denoted by this, and this thing you can calculate. So you can say, what is the, so I have a certain system, say this is about the energy, you have this energy opera, this is the spectrum of the energy. What is the probability that the measured energy lies within this subset E? That's something you can calculate. Now, if you're here in the domain where you have these discrete values, you can, of course, well, not of course, but it turns out you can make this E small enough so that you can get the probability that you get this, because there's nothing else in here. But if you're in a continuum, it would be very silly to ask for the probability that you get exactly this value. You know this? You have an antenna, a fly comes, and it sits down with equal probability anywhere on there, for whatever reason. And then predict what is the probability that it sits down exactly there. Well, the probability is 0, right, because it's a continuum. But it becomes meaningful if you say, what's the probability that it sits down in a certain interval, right? So that is this whole idea with certain intervals, and there where it's discrete, this reduces to the probability, right? So, but you see, the fact that in quantum mechanics you have to, at the same time, deal with values that can be discrete, have a discrete part, as possible values that have a discrete part and a continuous part, requires that we have one type of mathematics that copes with both. And this measure theory is that type of mathematics at this level. Okay? And what I tell you is that you can always get this measure, you can always calculate this measure here from a self-adjoint operator, an observable, and from a state. I'll tell you in a second how states are modeled. And only this probability can be calculated. Okay? So you cannot say what will the result of, will you get this value or will you get that value? So, well, with 20% probability you get this, with 100% you get this. Okay? Let me make a remark before I forget it. I should have made this earlier. When you have this Stern-Gerlach apparatus, in the past it was very difficult to send individual atoms in and electrons and so on. But today we can do that. And it's not that there is kind of one single atom is being smeared out. It's not the case. You shoot it in, and if you send in a single one, then it will plop, end here. And once you observe it, you know, pop, it ended there. That's it. So it's not one is being smeared over two positions. Sometimes people argue, yeah, well, it's the wave-particle duality, and it goes in, and then there's the smeared out. No, no, no. One goes in, and click, that happens. Do this experiment again. Blick. Aha, again. Do it again. Blick. Say, it always comes out. Blick. No, now comes one down. And in the long run, it's 50-50. Okay? Very important to not think that there's something being, one particle is smeared out into two. This is totally not true. Nevertheless, you do the experiment, and once it came out, you know where it came out, and then you know, oh, this is the Z up observable or something like this. But you cannot predict which is going to happen. There are exceptional cases. For instance, if you put two Stern-Gerlach apparatuses of the Z type behind each other, you know what's going to happen here. You know only Z up are coming out because you prepared the whole thing like this, okay? So you can prepare certain states where you know the outcome because the probability is 100 to 0. Well, if it's 100 to 0, you know what's going to happen. But generically, you cannot say which is which, okay? Okay, anyway, so that's side one. Only this probability can be calculated. In particular, one cannot predict which concrete outcome an isolated measurement will take. Well, the only thing is, you know, if this is the spectrum of the operator that you have there, you could never have an outcome that's not contained in the spectrum. Well, that's not possible. But you will not know which of the remaining ones, if it's more than one, will actually happen. This is even more annoying This is even more annoying. I'm sorry. This is even more annoying since the impact that a measurement has on the state of the system. So remember, this we discussed under point 2. This is already point C, what can be predicted. Under point B, we discovered if you make a measurement, it will have an impact on the system. Well, it could be that whenever I measure the energy, it has this and that impact on the system. No, it's worse. So I try to measure your momentum, right? So it could be that every momentum measurement pushes you in a certain direction. That would be kind of under control. It's worse. I measure the momentum. I have only a probabilistic outcome that I can predict what will happen. But how your state is changed by the measurement depends on the outcome that is really observed. It's either this or that, and you will be changed differently. Your state will be changed differently depending whether this comes out or that comes out. But which of the two, can only say with that probability you're going to be changed like that, with that probability you're going to be changed like this, but I cannot predict before how the measurement will change your state. That's terrible. Okay? It's even more annoying since the impact that the measurement has, since the precise impact, I should say, so how exactly it impacts the state, since the precise impact that the measurement has on the state of the system, CB, depends on the concrete outcome, so the concretely measured value of that measurement. Well, you can imagine, if all of this is true, and we don't know an example where it's not true in nature, if this is all true, the worldview that follows from this and the effects in the phenomena that subject themselves to this kind of, well, principles ways, that will be a very different world from how we know it. I look where you are. Well, what do you mean? What do I mean by this, right? I mean, and I change it thereby, and I don't really know what comes. It's terrible, okay? Well, it's terrible. Other people say it's beautiful because it's nature and so on. But as a classical physicist, you say, I mean, this is really, it's a disaster, right? So you see, it's not so bad if the classical mechanics course didn't go so well because it's all wrong. Okay. So that's the reason why we teach first classical mechanics and then quantum mechanics. So, okay. Good. Okay. Well, and another fact is, of course, the probability that a system in the state rho, if you measure A, that the outcome will be something in the possible outcomes is 1. All right, okay. 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 So, so this ends my short overview. And again, it doesn't claim to be complete. It doesn't claim to have in it all the seeds that you need for the axioms we're going to write down. And in fact, I argued it probably cannot even have all in it that we will write down in the axioms, because the axioms are given in a very certain precise formulation, right? And there certainly are other formulations that produce the same experimental results. So you cannot derive the formalism from the observed results, right? It's a naive idea. You look into nature and then you make the theory. It's different. You look into nature already with an idea of a theory. And okay. Anyway, so we're not going to discuss this. But all I say, crazy stuff like this, crazy from the point of view of a classical physicist, needs to be accommodated in what is to come. And it justifies throwing away really everything we had in classical mechanics. And so V is wrong. A suitable theory, which up to today is still the prevailing theory, a suitable theory that accommodates all known experimental facts does it? So you see, what does it mean? People say this, oh, everything we know is accommodated for. Well, maybe there are some things that do not follow from this, but that we, in a sense, explain nevertheless with it, but we explain it in a wrong way. It wouldn't be the first time in physics history that true facts are explained the wrong way and are taken as support for the theory. Okay? It could be that in the future, certain things we will understand in a different way, and we say, oh, how could we not see that this is not really blah, 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 blah. Okay? So this should always be on your mind, but of course not in the examination. For the purposes of this course, all I tell is true. Okay. A suitable theory that accommodates all known experimental facts has been developed roughly from 1900 to 1927. On the physics side, well, of course, it started with Planck. Do you know the story? Well, read up on the story. There are good books on it, right? I mean, it started with Planck and then Bohr and so on. But really, if it comes to mathematics, if it comes to the formulae you find in books, it's essentially Schrödinger, Heisenberg, and Dirac that gave the theory its shape. And on the mathematical side, it was very early on seen by von Neumann that whatever equations are written down there, they need a very proper mathematical foundation. And for Neumann, well, it's always wrong if you say single-handedly, so I should write in both cases and others, and we're academically fully correct, without adding any information whatsoever, and others, okay. On the mathematical side, by von Neumann, he invented a massive proportion of what today is known as functional analysis, because he realized that as little as you can write down Newton's theory without knowing what a derivative is or a manifold, as little can you write down quantum mechanics without knowing the basics, and sometimes a little more than the basics, of a field called functional analysis. And the first half of this course will consist in the functional analysis we need to develop to even understand what we are talking about. Okay? This deviates not from all, but from virtually all textbooks on the market. But in this case, there are textbooks. And next time I'll give a list. There are very few textbooks that do it in this mathematically clean way. Now, there's always the question in physics, do you follow a mathematically rigorous path and then run the danger of not seeing the forest for the trees? Or do you give more an intuitive picture? And, well, first of all, it's my belief, and that of a number of others, that only what you can state clearly, right, can actually be understood and discussed and maybe falsified. And second, quantum mechanics is so non-intuitive, you can write down simple mathematical explanations for this stuff, thinking it's all behaving like matrices and it's just all linear algebra and it's just vector spaces as normal and so on. The fact is simply not true. It is simply absolutely not true. Actually, apart from the spin 1/2 system with spin up-down, that is mathematically correct in the way this is written down in most even theory textbooks. But if you want to do things like the harmonic oscillator, where the spectrum is not bounded, so in the up-down, the spectrum is bounded. This result and that result on the real line, these are the set of values is a bounded set, right? There's an upper bound and a lower bound to it. But as soon as the set, even if it's still discrete, like say the energy of the harmonic oscillator that starts somewhere and then goes up like this, goes up and up and up and up. It's an unbounded spectrum. And these operators, so these observables that have such an unbounded spectrum, they do not fit in any way into a matrix picture of observables or something like this. Okay? It gets even worse if you look at the hydrogen atom, where a part is discrete and then there's a continuous part to it. Also, this doesn't fit into what normally people say. You look at the eigenvalues of the operators. Have you heard that? I don't know, you have, huh? Stuff like this. Yeah, for the discrete spectrum, this is true, but for the continuous spectrum, it fails to make any sense in the first place. Okay? So, and if you then think of one of the biggest problems that people think they must solve, namely the quantization of gravity, even if you start with this very simplified quantum mechanics, you will not survive the first day of calculation, because simply quantum mechanics, and von Neumann figured it out almost 100 years ago, right? So in a sense, you can say the philosophy of the course is I refuse to teach you something that's different from what was already clarified 100 years ago. Okay, so we will do it what one arguably from a mathematical point of view calls the proper way. The antidote, and we'll do physics, that's not it, and I will give a mathematical presentation with mathematical arguments. In fact, it will be definition theorem proof, with very few exceptions, okay? But it's the only way to actually deal with the objects. If you don't see the proofs, you can never calculate a concrete example. How would you? You don't know how you deal with this. It all becomes blah, blah, okay? Of course, I will always allude to the physics, and I will only pick from all that can be done here, I will only pick what leads in a direct way to the physics. But anyway, it's an integrated course, so the antidote to the theory part is the experimental part, right? Where you will see all these things, in order to make progress there, you just use them in a certain way, and very often you will say, that is what he writes, but what he really means is this, okay? No, I mean, of course, this is known also to the other lecturer, right? But one needs to know both sides as a working physicist, right? But if in doubt, and if you later on try to do new theory or work on difficult problems, you know where to come back to, okay? You're not left alone. Okay. So this concludes the exposition of what we want to do. And there will be problem sheets, of course, and these problem sheets will be rather extensive in the number of problems usually, but the problems will be very simple usually, and one reason why they will be a bit more extensive in number of problems is because I will always let you solve problems that I want you to solve for the idea of the ongoing theory course, but there will always be more or less one page where you work out the simple version of what we do in general, okay? And the simple version actually only applies to systems with finitely many measurement results, which apart from spin 1/2 is almost none, okay? But then the formulae derived, there are the formulae you find in the textbooks which are there applied to all the other systems as well, somewhat unjustifiedly. But of course they're applied in such a way that things work out fine, okay? But for you it's important to know this is not really the truth, okay? This is just the wrong formula applied in a way that you're not hit over the head with a hammer for doing that, okay? Anyway, so we're trying to, so there are several courses in one, okay? Good. Section 2 is the axioms of quantum mechanics. So as I said, I will first write them down in this unknown language or partly unknown language to you, and then I will explain the most relevant terms by little clouds, and we'll come back to this. Okay, so nothing I write down now is not complete or not true, but of course I cannot now work out in one lecture all the consequences. So the axiom 1 is the following. With every quantum system, there is associated a complex Hilbert space. I'll explain in a second what a Hilbert space is. Is associated a complex Hilbert space, but we say if I underline it as an unknown notion, and that is actually a tuple consisting of a set H, an operation plus an operation S multiplication, and a so-called sesquilinear inner product. I'll explain that in a second. With every quantum system, there is such a Hilbert space associated. This axiom continues, the states of the system. So you see, I talked about states before, appealing to your intuitive notion of that is what the system is like at the moment or something. Okay, but careful. The states of the system are all, so they're all possible, are all positive trace class linear maps rho that are linear maps from this Hilbert space into the Hilbert space. So they're positive and they're of trace class and they're linear. Linear you might know for a vector space, but what is positive and what is to be of trace class? We'll say it in a second. For which, now comes the final condition, for which the trace of this map, and I explain to you what the trace of a map there is, equals 1. To be of trace class means that the trace is defined in the first place. Now you say, well, you always have a trace of a linear map. Well, yeah, on a finite dimensional vector space, sure. But if it's an infinite dimensional Hilbert space, like for the quantum harmonic oscillator, like for the hydrogen atom, well, like for just anything but the spin 1/2 system or spin 3/2 or whatnot, kind of toy stuff, okay, you always have an infinite dimensional one. So it's very important that this is of a trace class. Whatever it means, I'll explain. Now, that's the end of the axiom. So the axioms get what I declare to be a square. Okay. A remark is the following. I mean, really throughout the literature, it's almost everywhere, sometimes people, or often people say the normalized elements psi of the Hilbert space. What does normalized mean? Well, you have an inner product, and normalized means that the inner product of this with itself is 1. Okay, that is what we mean by normalized. Almost everywhere it is stated. Almost everywhere it is stated. The normalized elements psi and h are the states of the quantum system. False. It's just not true. These are the states of the quantum system. Terminology. A state is called pure. It's called a pure state. And if it's not pure, then it's defined as a mixed state. Well, it's called a mixed state. A state is called pure, a state rho. Of course, if I say here state, whenever I use state, I use this definition of state, not the one. So let me put this in quotation marks. A state rho is called pure if there exists a psi in the Hilbert space such that, so what is a state? A state is a linear map from H to H. Well, as a linear map, I must say it takes an alpha and it maps it to an element of H, rho of alpha, and this rho is called pure if there exists a psi in H such that the rho can be expressed entirely in terms of the psi, namely like this. Okay, so this is just the one you plug in to get something out, but this is the thing. So there is, for pure states, so thus, for pure states, it is true that a state is associated with an element of the Hilbert space. But there are many, 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 many different psis with which it is associated. So it's not a one-to-one thing. So to say the states are these normalized elements, even if normalized is still many psi that correspond to this one state. And it's simply not true that the normalized elements of psi would uniquely label a state and hence deserve to be called a state. And even if they did, they would at most label the pure states. But there's also something called mixed states. What that all means you'll learn later. But states are pure or mixed, and that is what they are. Okay? So the elements of the Hilbert space are not the states of the system, although it's very often stated. Please refer to Axiom 1. Right, so let's give some definitions. Let's first look at the, okay, you know what? I know you hate it, that is why I'm going to do it. I will not wipe everything. I will just not wipe the notions I want to explain. State, we said. Okay. Positive traceless linear maps, okay. For which to trace. Good. So these are the underlined notions that I didn't explain. So, no, okay, it's childish. I'm not going to do it. Sorry. Good. It's the stuff you come up with when you sit and drink coffee and you think it's a good idea. Okay, anyway, so we're talking about a complex Hilbert space. So I should have the heading some definitions. I just want to explain some of the notions that occur, although later on I could give them in the further development of the course one by one, but probably already on the next problem sheet, I will ask you to work this out in simple cases, so I better provide it. Okay. Is there a question? Okay. So a complex Hilbert space, we said it's such a tuple consisting of a set H and a plus and an S multiplication and a sesquilinear inner product. So what this is, it's H is a set, nothing more. The plus is a map that takes two elements of the set, H back into H, and the times is a map that takes a complex number, and this is why this is called a complex Hilbert space, that takes a complex number, an element of H, and takes it back to H, in such a way that this set with these two operations satisfies the vector space axioms, namely the axioms of a C vector space, and that is Caney and Adu. Commutative, associative, neutral, inverse, and these tie these guys together. They're these 8 axioms. If you don't know them blindly by heart, waking up in the middle of the night, review them. So this is the first part here. It's a complex vector space. All right. Now, what is this? So that's the first ingredient for a complex Hilbert space. The second ingredient is this guy here. That's the so-called sesquilinear. Sesqui means 1.5. It's sesquilinear map. These are open slots. You can feed into it two elements of the set, and you produce a complex number, again, because we're dealing with a complex vector space. And this sesquilinear map has several properties. The first property is that if you have a phi and a psi, for any phi psi, I'm not only writing down, always writing down for any, if you take these and you switch the order, you get a complex number, but you get the complex conjugate. And in this course, the conjugate will be denoted by a bar. Sometimes I will write a star. Please tell me then to write a bar, because the star will be reserved for something different. Then 2 is it's linear in the second slot. That means if you take here a psi 1 plus alpha psi 2, where the alpha is a complex number, actually any complex number, then you can pull this apart. This will become phi psi 1 plus alpha times phi psi 2.
I'm just
Yes.
wondering if you what is the axiom you add to get to the scalar product? It's normalization.
This is the scalar product.
Yeah,
Or you mean the
scalar
S? Well, this is the S multiplication. This is the scale. What is it?
Scalar product. You add
There is
some
none. What do you mean by ordinary?
Yeah, it's the one maybe you learn at school or whatever.
Ah, no.
You add one to get there. Was it the normalization? I wonder.
No, the normalization is with this one.
Okay, then.
So this is the one, there's no other. It's the S multiplications on this is the scalar product. It's the sesquilinear inner product. Okay, has this property. Because of the first property, if you do this in the first entry, then an alpha bar is pulled out. Okay? Okay, so this is this. That's the linearity or the sesquilinearity. So this is called the Hermitian property. This is the sesquilinearity. And then we have the positivity that psi psi is greater or equal to 0 for all the psi in H, and the equal sign is assumed if and only if psi is the 0 vector in H that is guaranteed to exist because of this. Okay? That's a sesquilinear map. And now you say we have all the structures that appear in this quadruple up here defined, but there is an additional requirement on Hilbert space. And there's yet another one which we'll only introduce later. The requirement is that this sesquilinear inner product space is complete. So the third ingredient and requirement you need to check, and in the future, so I always think, oh, I need to check it, but in the future you're allowed to use, that's better, is that the space is complete. Completeness. What does that mean? Completeness means if one has a sequence in this H, what is a sequence? A sequence is a map that takes the integers to the space. Because then for every integer, there's an element of the space. If one has a sequence in H that we call phi, which satisfies the so-called Cauchy property, or sometimes one says it's a Cauchy sequence, which satisfies the Cauchy property, namely, what is this property? Namely, for every epsilon greater than 0, so obviously real, there exists an n in the integers, a capital N in the integers, such that for any pair of integers which are beyond this one, it is true that the norm, I explain that in a second, of the nth member, so I denote this phi n, and the mth member is less than 0. And at this point, I need to tell you what the norm is, but you already gathered that from the axioms here, in particular from the third one, you know you can define a norm of psi as the square root of psi inner product with itself, because the square root will always be defined, and the norm now really takes you from the Hilbert space into the real numbers. Okay? And you know there are further conditions for a norm, and they're all satisfied by virtue of these axioms for the inner product. So from the inner product, a norm follows. The opposite isn't true. There is not for every norm, there is an underlying inner product that induces it. That is only the case if the norm satisfies the parallelogram identity. That's absolutely correct. Okay, fine. But here we start with this, so let's not worry about it. So the completeness means if one has a sequence of which one knows that if the sequence goes on, and you're far enough into the sequence, the elements of the sequence no longer lie further apart than any prescribed epsilon. It's a kind of a weak convergence requirement, but completeness means this suffices. If one has one may already conclude, and that's something special. One may already conclude that the sequence converges in H. In H, right? You can have a Cauchy sequence on the, say, rational numbers, but it will not converge on the rational numbers because the limit may be square root of 2, which is outside the rational numbers. But the real numbers, they are complete. Any Cauchy sequence in the real numbers will converge against an element of the real numbers. That is, so actually converges, that's a different criterion. That means there exists a phi in the space itself, not in an extension of the space, not in a completion of the space, which would be a completion of Q. No, but in a space itself there exists an element phi, such that for every epsilon greater than 0, there exists an n in the natural numbers, such that for all n that are larger or equal than this n, the norm of the difference of this phi and the nth member of the sequence is less than epsilon. Well, it converges. It converges in the standard topology on H that has been induced from this norm. Because if you have a norm, you can build the softballs. If you have the softballs, you induce the standard topology. So I could have written the sequence converges in the standard topology on H that has been induced by the norm, which has been induced by this inner product. Okay? Whenever you have a convergent series in any space, it is automatically a Cauchy sequence. But that from Cauchy you can already conclude that it converges, that's something special. And that's something we require of the Hilbert space. Okay? And that will be very important in many proofs. In many proofs, we will very quickly see that something is a Cauchy sequence. And we say, but then it converges. That's great, okay? So it looks like, it's complicated to check. Later on, it will help us to make conclusions we otherwise couldn't make. And all you have to do once you start working with the Hilbert space that you say underlies the quantum system, because that's your model of the quantum system, you need to make sure that this works, that this is true. Okay, so that's the Hilbert space. Then there is this notion, and this is the final definition, so there will be no further adaptations. Everything I tell you here, you can learn, commit to memory, and not forget. Okay? These are very important notions we're going to work with, but we will revisit all of this, and we will have examples and examples on problem sheets and so on. Okay? So you really need to wrap your head around this. This is going to stay very important. Okay, so this is this Hilbert space concept. And, right. So you see, this looks very different from manifolds, right? I mean, where on earth are the manifolds here? They're not there, right? Later on, for specific problems, there is a field that's called geometric quantization. It asks the question, if I hand you a manifold that is the phase space of a classical system, a symplectic manifold, and I hand you a function on it, a continuous function on it, a classical observable, if I put that on the table, the field asks the question, how do you construct from these classical data, how do you construct the appropriate Hilbert space? The axiom says, to every quantum system, there underlies a Hilbert space. Well, which one? How do you construct it? It's a very difficult question. That's the question of quantization. You start with a classical system and you make it into a quantum system. Are you classical?
I think not.
No. It's a very strange question, because what do you mean you start with a quantum system and you make it into a classical system, you make it into a quantum system? Quantum theory is more than the classical theory. If there was a map that you could take the classical problem, translate it into a quantum problem, in a sense, one-to-one or uniquely, well, you very likely would be able to calculate it classically and then only translate the result, right? In fact, this goes a long way, this quantization idea, but essential things do not really work out like one would like them to work out. It doesn't mean that this is not a very important subject to answer the question, well, but now for an oscillator, which Hilbert space? I'm not answering this question with this axiom. You have to keep that in mind. So don't be discouraged at this point if you don't know how is to the system, the Hilbert space, how does it arise from the system I have in hand? At the end of the day, it's a modeling question. Okay? Anyway, we'll come to that. Okay. So I just try to point out what you're not supposed to understand because it wasn't said. So now I also talked, this was the first part of the axiom. The second part of the axiom talked about linear maps. Now, of course, you all know from vector space theory, from linear algebra, what a linear map is. Nevertheless, I write it down again. A linear map is a map A that goes from, well, not from the vector space into the vector space. It goes only from a domain which may be a proper subset of the vector space into the vector space. Okay? It goes from a domain here into there. Okay? And we will only look at densely defined linear maps. What does that mean? Well, it means that the domain is a dense subset in the vector space. So that means that for every element psi in the vector space and for every epsilon greater than 0, there exists an alpha in the domain of the map such that the norm of the difference of alpha and this element psi in the full vector space is less than epsilon. You can always, not every element in H is in dA, but for every element in H, you find one in dA that's arbitrarily close. Like Q is dense in R. The rational numbers are dense in the real numbers. So this is a little cloud. And we will only look at densely defined operators. So the dA, the domain, is always dense in here. In linear algebra, you probably always look at maps from V to V, or from V to W or something. But those were full vector spaces. This only needs to be a domain. And this becomes important for infinite dimensional vector spaces. For finite dimensional ones, you can always take the entire vector space. And for bounded operators on infinite dimensional ones, you can always take the entire vector space. We'll come to this. But for the unbounded ones, like think energy of the harmonic oscillator, energy of the hydrogen atom, this will be it will be a proper subset of this H, but it will still be densely defined. It's a very important notion. Okay? Okay, so this is a linear map, and of course linear means that if you apply it to phi plus alpha psi, then you can pull it apart. This is A of phi plus alpha A of psi for all, well, you know, alpha in C and phi and psi in H and so on. That's a linear map as usual. A notation that's very often used, and which we're also going to use more and more, is that you actually write A psi instead of A applied to psi, simply in order to spare some brackets. Okay? So we'll just A psi. A acts on psi. What does it mean it acts on? Well, it means A is a map, and it's fed a psi. That's it. So let's not confuse ourselves with new terminology of something acting on something. It's a map. Okay, that's the notation. It's a linear map. Now, there is the notion of a positive linear map that appears in the definition of state. A positive linear map is a map such that for all psi, well, in the domain of A, where else, for all psi, it's true that psi, A psi, there I use the notation, is greater or equal to 0. So they would rather be called non-negative maps, but it's tradition to call them positive maps. Okay, that's it. And then there's the final criterion which I gave, and that is that the A is of trace class. A being of trace class, there are different formulations for it. The one that's maybe in practice not always the easiest one to evaluate, but it's the easiest one to understand, that suffices for the purposes of the next few problem sheets. And it's the full definition, is A is of trace class if for any orthonormal basis En, where the n come from a suitable range, okay, for a finite dimensional vector space, E1, E2, E3, but to E dim H, right? For an infinite dimensional one, it's E1, E2, E3, E4, E5, E5. And the question is this basis countable? Can you even label it by an integer? If it is, it's called a separable Hilbert space. We'll work on that later on more probably. So if for any ON basis where the n goes over a suitable range of the Hilbert space, the series, the sum or the series, and there you see the issue. If it's a finite dimensional Hilbert space, then the n will run from 1 up to, so it goes over all n. If it's a finite dimensional one, it will just be a sum of dim h many terms, namely of En with A En, if this sum is less than infinity. Well, I mean, if this is a map and if this is on the domain. Okay, now we have A is of trace class, and now we need an A that is defined on the entire Hilbert space. So the domain needs to be the entire Hilbert space, because otherwise you wouldn't know whether for any ON basis this basis vector happens to lie in the domain. But because the A acts on it, now I said it, because the A maps it, it must lie in the domain of A, because it's for any ON basis, I need to have an A, can only be of trace class if it's defined on the entire Hilbert space. Okay? But now it's a series if this is an infinite dimensional Hilbert space, which is the rule rather than the exception, and then this is not a sum, but it's a series. And for a series, it may well diverge, right? But only if it doesn't diverge, then if this is less than infinity, then the trace of A is defined as exactly the sum. So in other words, an operator defined on the entire Hilbert space is of trace class if the trace is finite for any ON basis that you choose. And then you can show not only is it finite for any ON basis, but then it doesn't even depend on the ON basis. That's a simple exercise. Okay, so this is to be of trace class. And that completes the first axiom. Axiom 2. The observables of a quantum system are the self-adjoint linear maps A, which each may have a different domain as long as it's dense in H, from A to H. And that's it. Those are the observables. The only question that remains is, what is this condition of self-adjointness? Now, this condition of self-adjointness is a very subtle one, very subtle. And it will take us a lot of work to really come to terms with this. In a finite dimensional Hilbert space, it becomes very simple, and you'll work that out on a problem sheet, and that is what's usually presented as the axiom. But that is really not true for unbounded operators, infinite dimensional Hilbert spaces. So this deserves a box. That's the axiom. But now it deserves some explanation. So definition. A linear map A, densely defined on its domain, is called self-adjoint if, now this is now simple, if it coincides with its adjoint map. Well, if it coincides with the adjoint itself, adjoint, that makes a lot of sense, with the adjoint map. And what is the adjoint map? The adjoint map is a map that's called A star. There is the star. Of course, nothing to do with complex conjugation, okay? Nothing. Nothing. I emphasize this because in most books they say, oh, before it was complex conjugation, now it's the star and it's somehow the same thing. And in a matrix anyway, if you also take the trust, forget it, okay? It has nothing to do with complex conjugation, at least not at this point. The adjoint map A star, well, it's defined on what domain? Well, on its domain, on D A star, okay? So the adjoint map can have a different domain, which we call D of the H star, into H. What does it mean to coincide? Well, to coincide means as a map, this is the same as this one. In order to be the same as this one, the first thing that must coincide are the domains, right? So to coincide means that dA star is the same as the dA, because if already the domains differ, the maps cannot be the same. And then, of course, on these same domains, also the A star acting on a psi must be the same as A acting on the psi, and the psi comes from dA, or it comes from dA star. It doesn't matter. It's the same. Okay? So actually, I don't need this explanation. I just emphasize it that coinciding means the domains coincide and the actual prescriptions for how objects are mapped coincide. Then an A is called self-adjoint. So self-adjoint makes a lot of sense. But what is the adjoint definition? And the subtlety is the definition of this adjoint. The adjoint A star dA star into H of a linear map A dA to H is defined by, we define this in two steps, and the first step is I indeed construct the domain. Well, if I want to tell you how it acts, I need to tell you what it acts on. So it's defined by the domain, and the domain of the adjoint consists of all elements in the entire Hilbert space. That's the reservoir from which we take this, because it needs to be a subset. So all the sign H, such that for all the alpha that lie in the domain of the original map, there exists an eta which can again be from the entire Hilbert space, and that's the special thing that you allow here so much. Such that the following is true, such that psi inner product with A alpha. Now you see alpha needs to come from the domain of A because A acts on it. Now you take all those psi's such that for all alpha on which the A can act, there is an eta in the whole Hilbert space such that the result of this action can be expressed such that this equals eta comma alpha. That's the condition. I'm sorry. Such that instead of letting the A act on the alpha here, you just leave the alpha and you somehow absorb this action by replacing the psi by an eta. One has to work a little with that in order to see what's happening. Second, you define the actual action of the A star on such a psi. Well, of course, the psi must come from here, right? This comes from here. You define it, well, you say for a psi, for alpha, there exists in eta such that this is the case. You define this as eta. And of course, there's only there exists one. You have to show that there is no other one, because otherwise this would not be well defined. We'll see. This is well defined. No, because whenever I define something in terms of something that I know to exist, I still don't know it's the unique one that does it, but one can show that is the case. That's it. So if you have a map and you want to check whether it's self-adjoint, you construct its adjoint in these two steps, and then you check, is this domain the same as the original one? Well, if it is, and the operator A is symmetric, well, one could define this, or one evaluates this, then you check this, and then you know it's self-adjoint or it is not. And it's very important. I could have written here something different. I could have written eta in dA. So instead of saying I look at any eta in the whole Hilbert space, I could look only for etas that also lie in the domain of A. That would be a domain that's obviously, possibly, I don't allow so much, so it's smaller. Because I say if there exists in eta, yes, so I allow more here. There would be a domain that's smaller, and that would not lead, defining the adjoint in such a way, would lead to the wrong notion of self-adjointness. If I say the wrong notion, what do I mean by wrong notion? Well, it would not be guaranteed that the spectrum of such an operator, which is the next notion we're going to define, or maybe next time, that the spectrum of an operator lies in the real numbers. In fact, one can show the spectrum of an operator on a Hilbert space lies in the real numbers, so the measurement values we would later on say in quantum mechanics are real, if and only if, not only if, but if and only if, the operator, the linear map that describes the observable, self-adjoint map, is self-adjoint. Okay? This is the key notion. For finite dimensional vector spaces, this is child's play. For not finite dimensional ones, it definitely is not. That is this. So please bear with me for 7 more minutes. Of course, totally owed to the blackboard erasing. Because I would like to complete the axioms, but I will be very quick now. Axiom 3. Chalk. The probability that a measurement of an observable A, well, now you know A is a self-adjoint map, on a system that is in a state rho, is in the state rho, yields a result, a measurement result, 20 joule, yields a result in the Borel set E, which is a subset of R, that will rely somewhere on the antenna, right, is given by, now is this object I told you can calculate it, now I tell you how to calculate it, is the measure associated with that observable in that state applied to the measurable set E, and it's constructed as the trace of an object PA of E, which I'm going to explain in a second, rho. This is a linear map. This is a linear map. There's a composition of linear maps. Often people call it a product of these operators, but it's a composition. First you apply this one, and then you apply that one. One linear map after the other is a linear map. Aha! We know that the rho is of trace class. We could take the trace of the row. Why? Because row is a state. A state was a positive linear map of trace class. Aha! But who tells you that the row after the PA is still of trace class? In fact, what we will see later, we will see that this object PA, which I'm also going to tell you what it is, but not how exactly to define it, we will see that this PA of E is a so-called bounded operator. Okay? And it's a fact that these two things, that the composition of a trace class operator and the bounded operator, it's a fact, we'll see, that the composition is again trace class. Oh, thank God, because otherwise we couldn't take the trace. Okay, fine. So you see, I mean, this looks terribly technical, but you can imagine what happens if you don't know these notions, then you start doing nonsense, okay? So this is this. The probability that you get a result measurement, if you measure A for a system in the state rho, the probability that you get a result within the measurable set E is this expression where, now it comes, this PA here is a map that goes from all possible Borel sets, from all possible measurable sets, all sets to which you can consistently assign volume, into the bounded linear maps on H. So we'll find this terminology later. Is the set, well, it's actually the Banach space. It's the Banach space, we'll come to this, of bounded linear maps on H. If I say operator, I mean linear map. It's a standard notion or standard terminology to call a linear map an operator, where this is the unique, that's important, projection valued, whatever that means, I'm going to explain that later, is the unique projection valued measure, so it's a measure in the measure theoretic sense, that is associated with a self-adjoint map, and only with self-adjoint maps. So if the map wasn't self-adjoint, we wouldn't have a chance to write this down. With a self-adjoint map A, according to, and now comes the key word, according to the theorem in which the first half of this course will find its climax, according to the spectral theorem. And I write it down, and it will be not understandable for you. The spectral theorem says that for any self-adjoint operator A, you can actually find projection valued measures, one projection valued measure PA, such if you then take with respect to this measure the Lebesgue-Stieltjes integral over all lambda, and you don't understand this object that I wrote down. You do not understand it. Then you can represent the A in this form. And this is the analog in the infinite dimensional case of the diagonalization theorem for symmetric matrices or Hermitian matrices on finite dimensional vector spaces. We know if a matrix is Hermitian, blah, 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 then you can find an eigenbasis such that you have only entries on the diagonal if you express the map in terms of the spaces as a matrix, blah, blah, blah. This is the infinite dimensional version. Imagine for the continuum, not even an infinite dimensional matrix would suffice because a matrix has only discrete eigenvalues. You could never get a continuum from a even bigger matrix, right? Hence, you need entirely new mathematics. It's the mathematics of the spectral theorem, and this will actually be a central result. And in the derivation of this result, we'll learn to deal with these types of integrals, okay? And what it actually all means. But what you see, if you have a self-adjoint map, you can get the PAs, and the PAs in physics feature here if you want to extract the probabilities. You need this. It's unavoidable. Okay, that is this. Now we have two further I'm very sorry for running slightly over time. This is just important to complete this here. So these were what I would call the kinematic axioms of quantum theory. They tell you about all the objects that you use and how you evaluate if you have the state and if you have the operator, so the observables. So this is the kinematics. And now follow two axioms, short axioms on the dynamics of the quantum system. And they tell you how a quantum system develops in time. There's a natural end to the lecture because of the chalk. Okay, so the axiom 4 is the axiom for unitary dynamics. And they prevail as long as, or during time intervals, T1 to T2, during which no measurement occurs. You remember, if you measure, then you change the state, but if you don't measure, the state changes, like in classical mechanics. There's just some evolution to it. And the axiom is that the state rho of T2 at time T2 and the state rho of T1. So this is new. Before we just called it rho. Now we make the rho dependent on a time because the state is at a certain time. Now rho, as it depends on time, at time T2 are related through, and now you will recognize this in a second, the rho at T2 is given by the u of T2 minus T1 times the rho of the T1 at time T1 times u inverse of T2 minus T1, where, now what is this u? Where the u of t is the following map. It's the exponential of I h bar h t h should be over h bar, of course. It's minus I over h bar h t, where this is the energy observable of the quantum system. It's the observable that gives you the energy. So you see the energy plays a big role for the evolution of the quantum system because the state is evolved like this. But the only question is, what on earth is the exponential function of a self-adjoint operator? Well, for that matter, what is a function of a self-adjoint operator? If this is a finite matrix, you can say, well, plug it into the series expansion of the exponential. For an unbounded operator, that's totally ill-defined. Okay? So, where? So again, we have a where if f is a function from R to C, that then the f of a is defined as the integral minus infinity to infinity f of lambda times dpa of lambda. And so here again, you use the PAs that come from the spectral theorem. So this is the second time we need the spectral theorem in order to write down this u, which is the operator that evolves the state. Okay? And like in classical mechanics, it's the Hamiltonian that makes the evolution of the state in this picture. Okay? So this is the axiom. This is just how this system evolves if there is no measurement. And the final axiom 5, so I'm sorry, I probably forgot with the last axiom to box it. Okay? This is just an explanation here. And the final axiom 5, you guessed it, well, it's called projective dynamics. or if you want to be more dramatic, you can call it the collapse of the wave function. Well, there's nothing collapsing, it's just the projective dynamics. And these prevail, or these step in place of the unitary dynamics as soon, or when a measurement is made at a time t sub m. So no longer is there the condition there is no measurement taking place, it's quite the contrary. It's when a measurement takes place. Then I need to tell you, I talked before about you, I look at your momentum, I have the momentum, the state, his state before my measurement, and there will be a state after the measurement. What is the state immediately after the measurement if I know the state before the measurement? Then the state rho after, immediately after the measurement of an observable A is rho after is given as the quotient of PA. There it is again, the PA. So I measure an observable A, and I again need these projection valued measures PA. Leave a little space. Rho before, then there's again a PA. And the rho before is, of course, state immediately before measurement. Because you see, if it's not immediately before or after, as soon as there's no measurement, then again the unitary dynamics take over. As long as no measurement, unitary dynamics, then there is a measurement, puck, projective dynamics, this rule, I'm going to finish it, and then again the unitary dynamics takes over, divided by the trace of the numerator, so that's just some normalization thing, but then here there's still something missing, of E. What is this? We have to state before, after, the time. We have from the spectral theorem the projection valued measure of the A, where, and that's what I mentioned before, where E is the smallest Borel set in which the actual outcome, that means you really did the measurement, the actual outcome of the measurement happened, I used the past tense intentionally, happened to lie. So that's what I said before. The way the state before the measurement is mapped to the new state not only depends on the A, on the observable I measure, momentum say, it also depends on what the actual outcome of the measurement was. But I cannot predict what the actual outcome will be normally. I can only predict the probability that it's this, which means I cannot predict how a measurement influences the state. I know if I know what came out, if I look at my measurement device and I say, oh, I measured his momentum was such and such, then I know how his state has been changed according to this formula. But if I don't read off what actually happened in this one instance where I sent this one hydrogen atom or whatever, then I wouldn't know. This is what I remarked before earlier, where I said, this is even more annoying. You remember? This is even more annoying that we cannot say which result is obtained, because the actual projective dynamics collapse of the wave function, whatever you want to call it, depends on that. That's axiom 5. And that concludes the axioms. With this, you can solve any quantum mechanical problem and develop the entire theory. The only thing that is left is to develop all the mathematics behind it, in particular the spectral theorem.